In this lesson, we're going to take a look at Avogadro's law and molar volume. So Avogadro's law is a relationship between the volume that a gas takes up and the number of moles of that gas. So we're looking at the volume of a gas, which is directly related to the number of moles of gas when the temperature and pressure are kept constant. So V1 over N1 equals V2 over N2. So if I start with 1 mole of gas and it takes up 1 liter at a certain temperature and pressure, if the temperature is kept constant, and to keep the pressure constant, if I double the amount of gas, then I would also need to double the space that is taken up by that gas. Otherwise, the pressure would not remain constant. So if in this volume I doubled my gas, then my pressure would also be increased. So in order to keep the spacing between those molecules the same, and therefore the pressure the same, at that temperature, I'm going to need to double the volume. Okay, so if I have 0.75 moles of helium gas, and that takes up 1.5 liters of space, then what volume will 1.2 moles of helium occupy if the temperature and pressure are the same? So I'm going to start here. The second or final volume is what I'm looking for. So I'm going to create my equation with V2 as my first variable. So V2 over N2 equals V1 over N1. So V2 over 1.2 moles equals 1.5 liters per 0.75 moles. So I'm dividing V2 by 1.2 moles. The opposite of that would be to multiply that. So I'm going to multiply that over to the other side. And that will cancel to give me my final answer in liters. And once I calculate that, 1.5 times 1.2 divided by 0.75, that is equal to 2.4 liters. All right, STP and SATP. So these are the volumes of gases at a certain temperature and pressure. So STP is standard temperature and pressure, which is at 0 degrees Celsius or 273 Kelvin and 101.3 kilopascals. SATP is standard ambient temperature and pressure, which is 25 degrees Celsius or 298 Kelvin and 100 kilopascals. Molar volume is at STP and SATP. We have the volumes that they take up. So the molar volume, the volume per 1 mole of gas at STP, so 0 degrees Celsius and 101.3 kilopascals, is 22.4 liters. So it doesn't matter what gas we have, 1 mole of that will take up 22.4 liters. And you can see here that 1 mole of helium gas, 1 mole of ammonium gas, and 1 mole of oxygen gas all have different masses because of the atoms that they are made up of, but they all still take up the same space. So here, the mass of the gas doesn't actually matter, and Avogadro was the first one to figure this out, although his hypothesis wasn't believed until about 50 years after he came up with that. So 1 mole of any type of gas at standard temperature and pressure will take up 22.4 liters. At SATP, so 25 degrees Celsius and 100 kilopascals, 1 mole of any gas will take up 24.8 liters of space. Okay, so we're going to take a look at how to use molar volume. So I can go in between a number of moles and a volume of a gas using its molar volume. So here, if I have 2.75 moles of nitrogen gas at STP, then I can use that molar volume to convert from moles to liters. So if I have my number of moles, then I'm going to multiply by 22.4 liters per 1 mole so that my moles will cancel. If I was moving in the opposite direction and I had my volume, then I would multiply by 1 mole per 22.4 liters, which would cancel out my liters and give me my amount in moles. So here I'm looking at this where I have my starting point is moles, so 2.75 moles of nitrogen times 22.4 liters per 1 mole because we're at STP. And that gives me 61.6 liters of space that 2.75 moles of nitrogen gas would take up at STP. Okay, so what volume at STP would 4 grams of methane take up? So we looked at number of moles. And if you recall from Unit 3, we have a relationship between the mass and number of moles of substance with its molar mass. And the molar mass of anything we can calculate. So if we have the number of moles or the mass of a substance, we can always convert to the opposite. So in this case, we need the number of moles to be able to figure this out. So my molar mass of methane is equal to 12.01 grams per mole for the carbon, and 4 hydrogens at 1.01 grams per mole each. So 1 mole of methane gas is 16.05 grams. So my number of moles then is equal to 4 grams divided by 16.05 grams per mole, which gives me 0.249 moles of methane. So 4 grams of methane is the same as 0.249 moles. And STP, this means that 22.4 liters is how much 1 mole of methane gas would take up. So I'm going to use that relationship here. So I have 0.249 moles. And I want to find the volume, so 22.4 liters on top and 1 mole in the denominator. And when I calculate that, that gives me 5.58 liters. So 4 grams of methane gas at STP will take up 5.58 liters of space. Okay, how many grams? So what's the mass of helium that's present in 8 liters of gas at STP? So STP, once again, 22.4 liters per mole. So I can convert my 8 liters using that ratio to a number of moles. And then once again, I can use my relationship between mass and number of moles to convert to mass. So the first thing I'll do then is 8 liters. And here I want to figure out how many moles. So this time my moles will go on the numerator and the 22.4 liters in the denominator. So that will cancel my liters, and it will tell me that the number of moles of helium gas there is 0.357. So now I need to convert from number of moles to a mass, which means I need my molar mass. And helium is just 1 atom of helium on its own, which is 4 grams per mole. So my mass is equal to number of moles times molar mass. So 0.357 moles times 4 grams per mole. And that gives me 1.43 grams. So there are 1.43 grams of helium in 8 liters of gas when it's at STP. So 0 degrees Celsius and 101.3 kilopascals. Okay, what volume in liters of oxygen gas is needed to completely react with 15 grams of aluminum at STP? So we started off with looking at the relationship between volume and number of moles, and then changing a volume or number of moles, we could calculate whatever we didn't know. We then looked at molar volume at STP and SATP, and then that brought back our number of moles and mass conversions. And here we're also going to look at balanced equations. So if I have 4 moles of aluminum will react with 3 moles of oxygen to produce 2 moles of aluminum oxide, I need to calculate how much this is in a volume, so how many liters that is. So what I have to start with is a mass of aluminum. So I have 15 grams of aluminum. I need to convert that to a number of moles because this is a mole to mole relationship. So I need to figure out how many moles 15 grams of aluminum is, which means I need its molar mass, so 26.98 grams per mole, and then my number of moles is equal to mass divided by molar mass, so 15.0 grams divided by 26.98 grams per mole. Grams will cancel, and that gives me 0.556 moles of aluminum. So the 15 grams of aluminum is equal to 0.556 moles of aluminum. So I need to figure out for that many moles of aluminum how many moles of oxygen I'm going to need. So I'm going to start with what I want to find. So my number of moles of oxygen for 0.556 moles of aluminum, and the relationship between those two is the same as from the balanced equation, and I need to make sure I have oxygen on the top because I have oxygen on the top over here, and then aluminum needs to be on the bottom. So 4 moles of aluminum, and to calculate my number of moles of oxygen, I'm going to multiply the 0.556 moles of aluminum over. So my moles of aluminum will cancel, and this will give me 0.417 moles of oxygen. So for 15 grams of aluminum, I'm going to need 0.417 moles of oxygen, and then I want to figure out what volume that is at STP. So 0.417 moles of oxygen, and STP, every mole will take up 22.4 liters of space. So I have 0.417 moles of oxygen, and then my relationship 22.4 liters for every mole. That's going to cancel, and my volume is 9.34 liters. So 15 grams of aluminum would react with 9.34 liters of oxygen at STP. Okay, one more. So what mass of iron would react with 5.5 liters of oxygen at STP? So here we are starting with the reverse, where we have a volume of oxygen. We need to convert that to a number of moles so that we can use our mole to mole ratio here, and then can convert a mass. And so why are we doing this? Well, gases we will often measure as a volume, and they'll take up a certain amount of space. And solids we will measure as a mass. So both of those can be converted to moles, and that will help us with the mole to mole ratio from the balanced equation. So we need to figure out then how many moles 5.5 liters of oxygen is. So I'm going to multiply that by 1 mole for every 22.4 liters at STP. And that is going to give me that is 0.246 moles of oxygen. So now that I know how many moles of oxygen that is, I want to figure out how many moles of iron would react with that amount. So that's my unknown, my number of moles of iron for 0.246 moles of oxygen. So from my balanced equation, I need iron and then oxygen. So iron is 4 moles for every 3 moles of oxygen. So my number of moles of iron is equal to 4 moles iron times 0.246 moles of oxygen divided by 3 moles of oxygen. Moles of oxygen will cancel, and that's going to give me 0.328 moles of iron. So 5.5 liters of oxygen at STP will react with 0.328 moles of iron, and then I just need to convert that 0.328 moles to a mass of iron. So for that, I need the molar mass. The molar mass of iron is 55.85 grams for every mole. So my mass is equal to my number of moles times my molar mass. Moles will cancel and I'll be left with a mass. So that's equal to 18.3 grams. So 5.5 liters of oxygen at STP is going to react with 18.3 grams of iron.